Hi everyone, welcome back. Today we're exploring a new data structure called heaps. And heaps are commonly used in an abstract data structure called a priority queue. As its name suggests, in a priority queue, the items that are in higher priority are dequeued first. So one very common use case for heaps are, for example, to organize numbers such that you always have the smaller number at the top of the heap. And the idea is if you have heaps like this, for example, a minimum heap of numbers, you're able to support finding the minimum number inside this heap using the top operation in this case. And in this case, this would be O1. If you wish to insert something into the minimum heap, it is very efficient as well. So in this case, insert would be O log base 2n. And if you want to pop something from the minimum heap, in other words, you want to take the smallest number from the minimum heap and remove it, in this case, pop would also take O log base 2n time. So because of that, the minimum heap is commonly used as a data structure to solve multiple technical interview questions. One very famous technical interview question that uses the priority queue is finding the median of data stream. I would link that to a separate video, but on top of that, you will also encounter that in pathfinding algorithms such as the Dijkstra's algorithm. And for our viewers who are interested in how Google Maps work, like that is usually a variant of Dijkstra's algorithm on top of that with additional optimizations. So what I'm trying to say is understanding heaps is important, especially because it's used everywhere. And if you are to do your best to find a position in software engineering or in tech, chances are you will encounter this data structure as well. So for today, we'll be exploring the fundamentals of what makes a max or a min heap, along with the properties of a max and a min heap. We will also show how we can express this heap in a single array using formulas to find what is the parent, the child, and stuff like that. And we also cover how do we insert an item into this max or min heap. In the subsequent videos, we'll be exploring how do we remove an item from the heap, as well as how to heapify a list to become a max or a min heap. So with that, let's get started. So let's go down to a fresh page over here and let's talk in the context of implementing a min heap. One way to implement a minimum heap is by using something called a binary heap in this case. So binary heap. And like its name suggests, this binary over here is a hint to binary trees. And binary trees are data structures, like its name suggests, it looks like a tree, it has branches and stuff. And binary trees consist of nodes like this, and each of these nodes can have up to 2 children. So it looks something like this. It has a left child as well as a right child. In the context of a minimum heap, this binary tree here would have some properties to them. The first property is that each node would have at most 2 children. So each up to 2 children. The second property is that this binary tree must be complete. You must fill up all the nodes at the front before you can start to fill up the nodes at the back. And spoiler alert, we would normally fill up the nodes from a level fashion like this, and we will fill up the nodes on the left before we fill up the right first. So if you try to add on a node like this is not valid because you are expected to populate the nodes on the left first. So we will go through that in a bit. So second thing is tree is complete. And the final one in this case is the property itself that makes that heap a minimum heap or a maximum heap. In the context of a minimum heap, in this case, the number at the parent, let's say parent has a number 7 over here, and it has number 13 and 15 in the children. In this case, this would be a minimum heap because the parent has a value smaller than both of his children. But if you're talking about a maximum heap in this case, then that's the opposite. You would have a number that is larger than the 2 children over here. And the operations of inserting a value and popping a value must ensure that this property is true for all subtrees inside this binary tree. So in this case, FYI, you can take this as a subtree and you can also take this as a subtree. And similarly, if it has children, the properties must be true for these subtrees as well. So yeah, that's pretty much it. So let's go back to the context of a minimum heap in this case. So let's set this to a number that is smaller than both of its children. And the third property is parent value must be less or equals to both child values, because this is a minimum heap. So this is pretty much the essence of binary heaps. So on top of that, we can also express this binary tree as an array. So let's take this tree over here and let's move it down here. And let's try to express this binary tree as an array. So I guess, okay, let me shift this down even further so that we have more space over here. And let's add on additional nodes. So let's say you have 20 like this. And now next question might be, how do we express this in an array-like fashion? So let's say we have an array that has up to 10 positions. 1, 2, 3, 4, 5, 6, 7, 8. 8 is fine. Okay, so we have 10, 13, 15, and 20. And as you might notice, as we discussed earlier, we would populate the numbers in a level-like fashion. And the nodes that are on the left side gets populated in the list first. And you can see that all numbers are filled up at the front. So in this case, we have a complete binary tree like this. Your next question might be, okay, then how do we... Oh, my bad. Okay, how do we... Okay, let me go back to this page here. Okay, how do we get the left and the right child index of a given number? So for example, let's say you're looking at the node 10 over here, and 10 in this case, the index is 0. How would we get the index of 13 and 15 in this array-like fashion over here? So we have a couple of formulas, fortunately. So if you want to get the left child index, this would be equals to 2 multiplied by I plus 1, where I is the index of the parent node you're trying to get it for. So let's do a simple example in this case. So now we can see that the index here is 1, 2, 3, like this. And if we plug in I equals to 0, we are getting the left child index of 10 after all. We will get 2 multiplied by 0 plus 1, and that gives us 1. And you can see that this corresponds with the left child of 10, which is 13 over here. Then for the right child, this would be 2 multiplied by I plus 2. And if we plug in I equals to 0, we will get 2 multiplied by 0 plus 2, giving us 2. And this corresponds with the index at the number 15. And these are pretty much the formulas. So the next formula is, how do we get, for a given node, how do we get the index of its parent? So for example, let's take a look at 13 and 15. How could we get the parent index for 13 and 15? So there is a formula for that as well. So the parent index will be equals to I minus 1 floor division 2. Okay, I guess I should make it clearer like this. So if we plug in I equals to 1, and I equals to 1 in this case refers to the number 13 in this case, the expected number is 0. So if we do 1 minus 1 floor division 2, we get 0. And if we do I equals to 2, which is the right child of 10, we would also expect an answer 0 in this case. So we will get 2 minus 1, floor division 2. 1 floor division 2 will give us 0. So we end up with the right answer of 0 in this case. So this is pretty much the essence of how we would represent a minimum heap in an array-like fashion, where we populate every single item into the array from left to right, level order. And we also went through the 3 formulas that allow us to still maintain this heap-like property by knowing how do we get the left child, the right child, and the parent index of a given node in this list. So now that we got this down, the next chain of thought might be, okay, now that we know how to express this binary heap as an array, how do we insert an element into this array then? So let's take this whole diagram over here and shift it down and put it here. Let's say we want to add in an additional number like this. So let's add in 1 in this case. So if we want to add in 1 into this binary heap over here, notice that the first step would be to add this 1 at the back of the array. And as you might see, this is the pictorial representation of this, just to reiterate again. But you might see that we have violated the property of binary heaps in this case. So you can see that the parent over here has a larger value than its child. So one way we can fix this is by implementing an operation called heapify up. Oh, oops. Okay, let me draw this. And heapify up, as its name suggests, is meant to take the final element that was just inserted and compare it with the parent. And if its value happens to be smaller than the parent, we will swap it with the parent like this. So we would compare 1 against 13. And since 1 in this case is smaller than its parent 13, we will swap them. So now we get 1 and 13 like this. And in this case, we can see that the property is achieved for this smaller subtree over here. So this subtree over here is pretty much a minimum heap right now. But we can see that the property for a minimum heap between this node and this node is not achieved. So we have to fix that. So how do we fix it? We would also recursively check this current node that we are at with its parent as well. So we will continue to do this swap till we reach a node that doesn't have a parent node anymore. So we will compare 1 and 10. In this case, 1 is smaller than 10, so we would swap them. So remove this, and let's put 10 here, and let's put 1 here. And just like this, we have successfully inserted an item at the back of the minimum heap, and we swap them around such that we achieve the minimum heap property even after inserting a number. So after we insert it, we can see that we have okay, I guess I should show the swapping in this case. So initially 1 was at the back, so what we did is we swapped it together with its parent in this case. So 1 in this case, like we'll be swapping with 20, 15, 20, 21. So 1 in this case would swap with 1 in this case. And what we did is we did a second swap between this one and this over here. So we get 1 and 10. And if we check all of the values in the list again, 1, 10, 15, 20, 13, yep, this is achieved. So this is pretty much how we would insert a value inside a minimum heap. So now, at this checkpoint, let's do our best to implement this in multiple languages. Now that we got the theory down, let's try implementing the skeleton for the minimum heap as well as the insert method to insert a value into the minimum heap. Let's start off by defining a class, the blueprint for creating objects of minimum heap. We would first start off with defining the constructor, the init method, and this init method would take in a max capacity. This max capacity represents the number of variables allowed inside this minimum heap. We will initialize this max capacity as an attribute of this object, and we will set it to the constructor's input. The next step is to initialize the size attribute, and this size attribute represents the current size of this minimum heap. We will also initialize a heap, and as we discussed, it is possible for us to represent minimum heaps with lists. So in this case, we will initialize a single list with the same length as the max capacity. The idea is for all items that are not inserted yet, or rather empty space, will represent empty spaces with none in this case. So let's also import some type hints, list optional, I guess in this case. This max capacity attribute will be of type integer, size will be of type integer, and this will be a list of optionals of integer. So yeah, that's pretty much it. Looks like we missed out anything else. So let's carry on with implementing the insert method. So the insert method, as its name suggests, is meant to insert a value, in this case an integer, into this minimum heap. And because this method is pretty much changing the state of self.heap, this method doesn't return anything in this case. The first step before we insert something is to check whether if the minimum heap is full. So to do that, we'll just do self if self.size is equals to self.max capacity. There's two things we can do here. We can choose to double the size of heap and copy all the existing values into this new heap, or for the sake of this demonstration, raise an exception object and pass in, yo, your heap is full. So in this case, if for the sake of this demonstration, let's just raise an exception for simplicity. But if it passes this check, the next step would be to add this value that was just passed to us at the back of the heap as we discussed. So self.heap.size equals to value. And notice that in this case, we're able to use the size as the new index of this value because it's 0 indexed. Like this list here is 0 indexed, so this size is pretty much the index of the new value. And of course, after you insert it, you must increment the self.size attribute by 1 in this case. And once we're done, the final step is to perform the heapify up operation on this new value that was inserted to ensure that the minimum heap property is achieved. So let's call self.heapify up, and we'll be implementing that in a bit over here. So this heapify up method takes in nothing, and it doesn't return anything at all. Its purpose is to mutate the state of self.heap such that the minimum heap property is still achieved. To be specific, it will take a look at the final item that was just inserted, compare it with its parent, and if its current value is less than the parent, perform a swap and continue to recursively do that till either we reach the top of the heap or the swap doesn't happen. So once the swap doesn't happen, it means that the minimum heap property is achieved. Lots of words, so let's get started. So the first step is to define the current index. In the first iteration, this current index represents the value at the index of the final item. So that's just self.size minus 1. The next step is to check whether if this current index has a parent index. So if current index, I guess self.has parent current index. This method is not implemented yet, but let me quickly define that as an abstract method so that we can implement that next time. So this is, oh yes, of course, I forgot the self keyword. These are all instance methods. So this is the, okay, let's just call this index, and this returns a boolean, and I guess I'll just implement it first. So let me also implement another method, get parent index self.getIndex boolean, sorry, is by integer, In this case, this method over here, get parent index, returns the parent index of a given index in this case. And the formula that we discussed in the previous step was that this is equals to index minus 1 floor division of 2. And using this method over here, we will just return self.get parent index is more than equals to 0. So if the parent index is more than equals to 0, then it has a parent, otherwise it doesn't. And that's pretty much it. So if this current index has a parent, then what we would do is we would get the parent index. And using this parent index, we can check whether if this current value is smaller than the parent. So we will do if self.heap current index is less than parent self.heap at parent index, then what we will do is we'll do a swap between the parent index as well as the current index. And similarly in this case, the swap over here is a method implemented by us. So we will pass in left index, right index, and it returns nothing. In this case, it's meant to swap the two items at the left and the right index with each other. So to do that, we will just do self.heap left index, self.heap right index equals to self.heap right index, self.heap left index. And that's pretty much it. So after we swap, then what this means is we have to recursively do that for the next iteration. Yes, I forgot one mistake here, which is that this operation here is recursive, so this should be a while loop over here. So in this case, once we're done, we'll set the current index to the parent index in preparation for the subsequent comparison between the parent above with its parent. So if this swap didn't happen, then what this means is that the whole heap already has the minimum property. So in this case, we can just return. So that's pretty much it from what I see. Okay, looks great. Okay, so now that we have this implementation, let's try to test this out. Let's create a main method over here. And inside this main method, let's define a minimum heap object and try inserting some values into this heap. And let's see whether if it maintains the heap property. So let's call this a minimum heap. This will be a minimum heap object, and we will call the constructor like this. We will also pass in a maximum capacity of 100 in a moment. And let's see, this would be the state of the minimum heap before insertion. Okay, let's try to print this out. Okay, I need to print out the attribute instead. Okay, so you can see that the minimum heap is initialized as a list of 100 none items inside here. The next step is to try inserting values largest to smallest into this minimum heap and see if the minimum heap was able to get the smallest number at the top of the heap. So for I in range 10 to -1, -1, this would insert values from 10 to 0 in this case. So let's do min heap.insert, let's pass in I, and let's try printing out the minimum heap again. And let's see if we got it right. Okay, size is not defined on line 13. Did I make a mistake here? Oh yes, of course. I was supposed to refer to size as an attribute over here. Typos happen all the time, man. Okay, let's, parent index, get parent index is not defined on line 21. Oh yes, of course, this is supposed to be an instance method. So I was supposed to use the self keyword over there. Okay, so looks great, 01529, but most importantly, the number at the front of the minimum heap is indeed the smallest number. So okay, that's pretty much it for this first video. In the next subsequent explanation, we'll be going through the logic of how to insert a value into the minimum heap, as well as the heapify method.